When testing the reasoning limits of large language models, researchers often encounter a specific blind spot. A model produces an intricate mathematical derivation, but makes a simple algebraic error halfway through and fails the problem. This graph illustrates the immediate problem. It compares the baseline accuracy of a state-of-the-art model on the AIM math benchmark against its accuracy when simply prompted to review its own work. Instead of correcting its mistakes, the model's performance actually drops. The standard approach to fixing this relies on external oversight. Engineers train models to self-correct by feeding them process supervision, step-by-step labels generated by human annotators or larger, more capable teacher models. That method hits a hard ceiling at the frontier of AI development. Once a model surpasses human reasoning capabilities, there is no reliable teacher left to point out exactly where it went wrong. Researchers at the University of Toronto have introduced a framework called ThinkTwice. It trains models to refine their own answers without any step-by-step labels or external hints, relying solely on whether the final, bottom-line answer is mathematically correct. A model can learn to locate and repair its own logical errors internally, provided the training pipeline optimizes specifically for the act of taking a second look. ThinkTwice builds on a reinforcement learning algorithm known as Group Relative Policy Optimization, or GRPO. In the first phase of this pipeline, the system draws a large batch of advanced mathematical problems from a training dataset. The central policy, the language model, receives a single problem and generates a wide group of candidate solutions, exploring multiple possible reasoning paths simultaneously. This diagram outlines the grading mechanism. Each candidate reasoning branch reaches a verification gate. An automated grader checks only the final boxed answer against the known solution, assigning strict binary ones and zeros for correct and incorrect outcomes. The algorithm calculates an advantage score by comparing each solution to the average performance of the group. If a specific reasoning path yields a correct answer while others fail, the model updates its internal weights to favor that logic. GRPO handles this calculation using only the main language model. Because it eliminates the need for a separate memory-heavy critic model, it drastically reduces the VRAM required for training. However, this efficiency comes with a specific data loss. When every candidate trace for a difficult problem results in a 0, the model extracts almost zero useful learning signal from that attempt. A failed trace might contain brilliant logic and one tiny arithmetic flaw. Standard GRPO treats the entire attempt as a failure, discarding the productive reasoning alongside the mistake. Phase 1 effectively optimizes the model to act as a first-pass solver, but it leaves the model entirely unequipped to evaluate or revise its own work. ThinkTwice addresses this by introducing Phase 2. Instead of discarding the failed traces from the group, the system feeds those exact traces directly back into the model as new inputs. The system constructs a refinement prompt by taking the model's initial flawed solution and appending a strict generic instruction. Carefully review your previous solution. The model must generate a second attempt conditioned on the exact reasoning steps it took during Phase 1. The reward system remains identical. The grader evaluates only the final answer. If the refinement reaches the correct answer, the algorithm updates the model's weights. ThinkTwice executes both of these phases, solving and refining, using the exact same policy backbone. This forces the network to maintain a unified parameter space. The mathematical logic required to solve an equation and the critical logic required to spot a misplaced decimal are integrated into the same weights. When Phase 2 successfully corrects a broken Phase 1 trace, it produces a rectified reward signal. The model successfully recovers the training value of a difficult problem that would have otherwise been a total loss. Because Phase 2 only requires evaluating the refinement traces rather than sampling a completely new set of varied paths, it adds only 3% overhead to the per-step training cost. By structurally looping failures back into the prompt context, the framework forces the model to use its own mistakes as the raw material for learning self-correction. This raises a distinct mechanical problem. If the reward is strictly binary, how does the model learn which specific sentence in a 3-page derivation caused the failure? It solves the credit assignment problem through the group comparison step. The model attempts multiple different corrections on the same base trace. Looking at this logic tree, we see the dynamic at work. One correction path alters a valid geometric proof and receives a 0. Another path abandons a flawed algebraic substitution, produces the correct answer, and receives a 1. The generic nature of the refinement prompt is crucial here. The system never tells the model whether its initial answer was right or wrong to begin with. This forces the model to develop an internal threshold for certainty, evaluating the structural integrity of its own logic, much like a human mathematician double-checking their work before submitting a test. If the training pipeline relied on explicit hints, flagging an answer as incorrect to trigger a review, the model would fail during deployment, because in real-world scenarios, the correct answer is unknown. ThinkTwice aligns the model's confidence with its competence, demanding that it verify its own steps using only the internal consistency of the mathematics. When we observe the training dynamics over time, a distinct pattern emerges naturally from the data. The researchers classify this as a rectify-then-fortify curriculum. This breakdown shows the model at step 100 of training. The refinement phase generates long, high word count outputs. It acts as a rectifier, actively repairing broken algebra and searching for missing structural logic in failed problems. By step 240, this behavior shifts. As the phase 1 solver becomes highly accurate, the refinement phase encounters mostly correct traces. It becomes a fortifier. The word counts drop dramatically as the model learns to compress its proofs, strip out dead ends, and present polished solutions. This two-phase optimization yields clear results on rigorous benchmarks like AIM and Math 500. On a 4 billion parameter model, the baseline reasoning score improved by 5 percentage points, but when allowed a single refinement step, the pass rate jumped an additional 11.5 points. Language models do not organically possess the ability to critique themselves, but by structuring the training environment to explicitly optimize for a second look, the ThinkTwice framework extracts verifiable self-correction from raw mathematical logic.